So in this video, we're going to take a look at one idea that you're probably familiar with, which is the Pythagorean Theorem. But then we're going to look at some I guess we would say special cases of the Pythagorean Theorem. There's a couple different, what we would call special right triangles, where the Pythagorean Theorem applied to those special right triangles gives us kind of an interesting result that can give us a shortcut in certain situations for figuring out missing side lengths on those special right triangles. So let's jump in first and take a look at the Pythagorean Theorem. So here we have it. You're probably familiar with the Pythagorean Theorem by this time. It's this idea that if I have a right triangle, right, it only applies to right triangles. We have to keep that in mind. And we call the legs of the right triangles A and B. Their lengths are A and B. Remember, the legs of a right triangle are the sides that make the right angle. So we'll go ahead and label those real quick. We have a leg here, and then we have another leg here. They form the right angle there. And if you call those lengths A and B, and then you call the hypotenuse length C. And remember, the hypotenuse is always the side that is across from where the right angle is. It's always the longest side of the right triangle. And we're going to call that length C. So we got A and B as legs, we got C as the hypotenuse. Then the Pythagorean theorem tells us that if we square each leg length and add them together, so A squared plus B squared, that will equal the square of the hypotenuse length. So we usually just think of the Pythagorean theorem as saying A squared plus B squared equals C squared. Again, some things to remember there is that it only applies to right triangles, that the side that's the hypotenuse is always C. Some people think that the side that you're missing is always what the C is, and that's not the case, right? Sometimes we'll be missing maybe one of these legs, and we'll end up with a number right there instead of a variable. So just remember that the C part of that A squared plus B squared equals C squared is always the hypotenuse. Now, if that's always true for right triangles, that A squared plus B squared equals C squared, then we can actually kind of make another conclusion, and that's what we're going to have in the next theorem. So what we see here is what we call the converse of the Pythagorean theorem. So remember, the Pythagorean theorem says if it's a right triangle, then A squared plus B squared equals C squared. So this idea lets you check to see if you're looking at a right triangle or not if you know the three sides. So if you have the three sides of a triangle, and you take the two smaller ones and square them and add them together, and that equals the longest side squared, then that means you're looking at a right triangle. So if the Pythagorean theorem fits basically in the triangle that you're looking at, then it must be a right triangle. And there's actually kind of there's more that we can tell. If the A squared plus B squared side is bigger, it means that it's an acute triangle. If you put everything in the A squared plus B squared equals C squared, and the C squared side ends up being bigger, then that means it's an obtuse triangle. But for our purposes, we're just going to be looking at whether or not, yes or no, is it a right triangle? And again, the answer is just based on whether or not the three sides can fit into A squared plus B squared equals C squared and make a true statement. Now, the next idea that we're going to look at is where we start looking at this idea of special right triangles. And there's two special right triangles that we're going to look at. The first one's called a 45-45-90 triangle. And a 45-45-90 triangle is otherwise known as an isosceles right triangle, right? So I'm going to kind of add to my picture here. I'm going to say that this 45-45-90 is basically an isosceles right triangle. It's an isosceles right triangle. Because if its measurements, so the 45, 45, and 90 refer to the angle measurements in that triangle. And the 90-degree angle is obviously the right angle. And then the other two angles are both 45. And we learned a while back that if your triangle has two angles that are the same, then the sides that are across from those angles would be the same. And so that means that in our 45, 45, 90, the two leg lengths are identical. They're the same length, and that's what makes it isosceles. It's got those two sides that are congruent, and then the third side is obviously the hypotenuse of our triangle. So for every 45, 45, 90 triangle, there's a pattern for the lengths of the sides. And one way to describe the pattern is to say that the legs will be congruent, so there'll be S and S, for instance, and the hypotenuse will be whatever that number is times the square root of 2. So in my picture right here, where I have my 45, 45, 90, where legs are s, the hypotenuse BC is going to be s times the square root of 2. One way I kind of refer to this idea is I say, all right, so if we have a 45, 45, 90 triangle, maybe like the most basic form of this 45, 45, 90 triangle is where each leg is 1, right? It's 1 unit long. Well, then the hypotenuse, the side, again, I put this 1 below the 45 because I'm saying, okay, the side that's across from the 45-degree angle, let's say that's 1. And then the side that's across from the other 45-degree angle is also 1. Then the side that's going to be across from the 90-degree angle, the hypotenuse, will be 1 times the square root of 2, which is just the square root of 2. And then from there, we can kind of scale this up or maybe scale it down to where we can say, okay, maybe it's not 1, 1, and 1 for the legs. Maybe it's 2 and 2. Then in that case, the hypotenuse would be 2 times the square root of 2. Or maybe they're 3 and 3. Then the hypotenuse would be 3 times the square root of 2. And we can kind of continue this idea. We can use any number we want for the legs, and then the hypotenuse would just be whatever that number is times the square root of 2. Now it does start getting a little bit trickier when we maybe kind of say, well, what if I have a hypotenuse that has a certain given length? How long are the legs? That does get a little bit trickier, but we're going to look at some ways that we can kind of figure that out fairly easily. So this is the 45, 45, 90 triangle theorem. Again, that's one of our two special triangles, and the idea here is that the sides kind of follow a pattern. 1, 1, and 1 root 2, or side, side, and side times the square root of 2. The other special triangle is what we're going to look at next. And this one's called a 30, 60, 90 triangle because it has angles that are 30 degrees, 60 degrees, and 90 degrees. So this one's maybe a little bit more complicated. We're not going to have legs that are the same length like we did in the 45, 45, 90, right? We're going to have one leg that's shorter than the other. And I know that this is shorter than this one because it's across from an angle that's smaller than this one is across from. And we learned a while back that if you have two sides of a triangle, if one is across from a smaller angle than the other one, then that one is shorter than the other leg. So this leg is shorter than this leg. So I think of it as we have a short leg and we have a long leg. And then we have the hypotenuse. Now there's a pattern for those. The hypotenuse is always 2 times the short leg. So if the short leg is s, then the hypotenuse right here, AB, will be 2 times s. And then the long leg right here would be that short leg times the square root of 3. And so in this picture, AC would be whatever BC is, s, times the square root of 3. So another way we can look at this and express it is I have my 30, 60, 90 triangle. And maybe across from the 30-degree angle is a side that's length is 1. Then across from the 60-degree angle will be a side that is length 1 times the square root of 3. And across from the 90-degree angle will be a side that is 2 times 1, which is just 2. And then we can scale up from there. So maybe across from the 30-degree angle, maybe it's not 1, maybe there's actually a side that's 2. That would mean that across from the 60-degree angle would be a side that is 2 times the square root of 3. And then across from the 90-degree angle, we would have a side that's 2 times 2, which is 4. Or if we went up to maybe 3 for the short leg, then the long leg is 3 root 3, and the hypotenuse is 3 times 2, which is 6. And we can kind of work off of this pattern here. Again, it gets a little more complicated if we maybe don't know the length of the short leg to start. Maybe we're given the length of the hypotenuse and we have to find the other two, or we're given the length of the long leg and we have to find the other two. And that's what we're going to be working on for, using this idea. But the basic idea here is that we have this pattern for the sides of our 30, 60, 90. The short leg across from the 30-degree angle is S. And then the long leg, which is across from the 60, is that number times the square root of 3. And then the hypotenuse, across from the 90-degree angle, is this short leg length times 2.